So in the last presentation, we looked at our carbone, which if you recall is the spearmint, and this was the caraway seeds. The structures of enantiomers are very similar, and many of their properties are identical. So this is their physical properties and not necessarily their chemical properties, but their binding sites. So the melting point of both of these is 25 degrees, and they also have the same boiling point. So we look at something like electromagnetic radiation that has perpendicular planes of electric and magnetic fields. The red electric field is the polarization of a light wave, and that is in one plane, while the magnetic field is in a perpendicular plane. So we have magnetic fields and electric waves that are in the fields, and there's one direction of motion of beam of light. Light traveling in the same directions have different polarization. So if you can see the figure here, this is unpolarized light that can go in all kinds of different directions. And when you have polarized light, it passes through a filter that polarizes the light, and then the orientation of the filter determines whether light is blocked or it passes through. In this case, over on this side, there's light that's passing through only in one direction and set up all of these directions here. If you have polarized sunglasses, the light will pass through that's unfiltered, and then it goes through your polarized glasses, and you can see here that all of those things are vertical, and so the light will pass through, and then you can see that. And that is when these are polarized in the same direction. If you have light that's unpolarized and it goes through the first filter, and then you have a second filter, no light is passing through. Here there's no light because this is a vertical filter, this is horizontal, so it's getting blocked through both ways. If you have polarized glasses, you can see different things or maybe see things better. If you're outside, the light filters a little bit differently. You may see different reflections in your windshield or your back windows, and certainly you can see fish better with polarized sunglasses. But you can see the differences here that they're showing you that light is filtered. With polarized lenses, it's not as bright. When plane polarized light is directed through a sample of a pure chiral compound, the plane that the light travels on will rotate. There's the light source, and then you have the polarizer that is fixed, and it goes through this tube, and it can turn. Your compounds will rotate in a certain direction in a certain degree scale. Compounds that can rotate plane or plane polarized light are called optically active. Enantiomers have opposite configuration, so they're S versus R, so they will rotate plane polarized light in opposite directions. You can see this scale here. Once it goes through the polarizer, something might go 45 degrees in one way, and the other compound will rotate the light 45 degrees in the opposite direction. For R2-bromobutane, it has the minus here, which means that it rotates the light to the levoratory direction, or left, and then positive is for the dextrorotary. So R and S could refer to the configuration of the chirality center, and the plus and minus refer to which way the light is rotated. And this number here is the degrees to which it is rotated, so 23.1 degrees. And there's no relationship between R and S and the direction of the light rotation, or plus minus. So just because this is R minus doesn't mean that all R is minus. So other relationships that we'll encounter are something called diastereomers. We can have isomers and then constitutional isomers, which have different connectivity. Stereoisomers have the same connectivity, and they're non-superimposable, so we can't stack them. We have enantiomers, which are mirror images of each other, and then you have diastereomers, which are not mirror images. This is a cis double bond. This is trans. Are these enantiomers or diastereomers? Well, these ones happen to fall into the diastereomer category. How do you figure that out? If we look at A and B here, this pair is a pair of enantiomers because they're mirror images of each other. And these are a pair of enantiomers. This is wedged, dashed, dashed, wedged. Those are opposite of each other. And if you notice, this has stereochemistry 1R2S. The enantiomer is going to have the opposite, so that becomes 1S, 2R. This is an enantiomer pair, this is an enantiomer pair. If it falls into that last umbrella here, it's not an enantiomer, it has to be a diastereomer. A and B are enantiomers. C and D are enantiomers. A and C, these are not enantiomers of each other. This OH is wedged on both of these, but it's not the same on here or the mirror image, so these are diastereomers. A and D are also diastereomers. B and C are diastereomers. So here in both cases the methyl is dashed and the OHs are different. And so they're not mirror images of each other, they are diastereomers. And then B and D are diastereomers. For a compound with two chiral centers, we can have 2 to n, or 2 squared equals 4 possible stereoisomers. The formula for the max number of stereoisomers is 2 to the n. N equals the number of chiral centers. So it's 2 squared, which equals 4. These are all of the combinations of this if you have 3 chiral centers. So for 2 cubed, there are 8 possible stereoisomers. So for the following structure, determine the number of chiral centers. So we're going to look to see which one has different centers. This is one. This is OH next to a carbon with a Br and a carbon. This is one. This is one. This is one. So for B, we're going to draw an enantiomer pair. So you can just give any stereochemistry here. I'm just going to do all of them wedged. And for the enantiomer, then they all will be dashed. Alright, so for C, draw a diastereomer pair. So for C, you just have to change the stereochemistry of one of those sites. So if I make this OH dashed, I can keep everything else the same. And that would be a diastereomer pair. Or this would be another diastereomer pair. Okay, so how many stereoisomers are possible? It would be 2 to the 4, which equals 16. So there's something called rotational symmetry versus reflectional symmetry. Something has a plane of symmetry. If we have these two compounds here, this one, when we draw it, this does not have a plane of symmetry. This one here does, so one half of the molecule mirrors the other. This has a plane of symmetry. Plane of symmetry also equals reflectional symmetry. And if you have this plane of symmetry here, this is achiral. So it cannot be chiral if there's a mirror plane within itself. So if you look at this molecule here in the trans, if you had this line here and you folded the molecule over, this would stack upon itself. So this one has rotational symmetry. And that is a chiral molecule. If it has a plane of symmetry within the molecule, it's achiral. If there's no plane of symmetry, then it is chiral. Meso compounds have that reflectional symmetry, and those again will be achiral. So if you draw this here, there's a mirror plane within this molecule. The compound that's meso has to have an even number of chiral centers, and it has to have that plane of symmetry, and it also has to be identical to the mirror image of itself. So this is an enantiomer pair. Neither of these are meso, because there's no plane of symmetry between them. But these two have the mirror plane. And if you do the stereochemistry here, this is S and this one is R, which if we flip it over is the same thing. So these are the same compound. So when you have a meso compound possible, you can't use just the 2 to the n. For possible stereoisomers, it's going to be less than that because these count as 1. So it'd be 2n minus 1. We have 3 possible stereoisomers. Fischer projections are used sometimes with compounds that have multiple chiral centers. Mostly in sugars is where we see these Fischer projections. So this compound here has 2 chiral centers. This one has 3. This has 4. And what this drawing means is that when you have these flat here, it's kind of like having these two groups pointing back and these two are coming at you. You can see the enantiomers here. They're mirror images of each other, and these are diastereomers of each other. So in sugars, if you convert an OH like this one to the other side, that can change the properties of the sugar as well. So to determine the stereochemistry in a structure like this in the sugar, we can't see wedges or dashes. But what you can do instead is you just pick one horizontal line as a wedge and draw one vertical line as a dash. All right, so we draw one horizontal line as a wedge. I'm going to choose the H so that I don't have to deal with flipping it again, and draw one vertical line as a dash. Then determine the stereochemistry. This would be 1, 2, 3. This would be S, but because the H is pointing forward, this becomes R.